Today we are going to discuss about the maximum likelihood estimator of the Poisson distribution. Among all the distributions like normal distribution, Poisson, binomial distribution, Poisson distribution is probably the most easy or probably the most easy distribution to estimate the maximum likelihood estimator. Okay, so at first I will write the Poisson distribution, the general form of Poisson distribution. Now Poisson distribution, which is the Poisson distribution, it is a function of lambda, because lambda is the only parameter present in the Poisson distribution. So I am writing L of lambda, that is nothing but function of lambda, and the function will be e to the power minus lambda into lambda to the power x, and this will be in a product form. So for denoting that product I have to give pi I starting from 1 to n. Here this pi is denoting that it is in the product form, and in the denominator portion I have to give x factorial. Now if I remove this product, if I remove this pi, and if I want to put this pi with this e to the power minus lambda, with this lambda to the power x, and with this x factorial, then it can be written as e to the power minus n lambda into lambda to the power summation x or summation xi. You may write it summation xi also. Okay, lambda is a parameter, so n is multiplied with lambda when we are taking the product. Xi is not a parameter, it's a variable, so that's why it is taking summation whenever we are taking the pi with the xi. And with this summation with this xi also, we are just xi factorial. With this xi factorial, this is xi factorial. As this is xi factorial, so we are not going to sum it, or we are not being able to do a summation with the xi factorial, so we have to just keep the product form, that is pi starting from I to n xi factorial. We have to keep the pi with it, with this xi factorial. Now we are going to take the log of both sides. After taking the log of both sides, we will do the derivative with respect to lambda, and then we will find out the value of lambda, that is basically the maximum likelihood estimator of the Poisson distribution. Now so we are going to take the log of both sides, that is log of L of alpha, and if I take the log of this portion, so e to the power minus n lambda, let me write it within the, let me write this entire thing in log at first. So it is nothing but log of e to the power minus n lambda into lambda to the power summation xi multiplied divided by pi ranging from I to on to n, sorry, xi factorial. Now if I take the log, and as you can see I have taken log here. Now this portion, this e to the power minus n lambda into lambda to the power xi, this portion will be completed. This is as you can see that if we do the log x to the power a into y to the power b, this can be written as ax plus by. You all know this type of transformation, this type of rules of law. So if I take this portion and if I want to write it in the general form, then this will be minus sorry, here I have made a mistake. It will not be log, let me write this formula properly. It will be a will be come out from the power, and a will become base, that is okay, but we have to write the log also, log x, log e base x. Okay, e is a base that is always there, even if we don't write it, it is always present there. Next is b will be come out from the power and it will become the base, and log e base y. So applying this same formula here, what it becomes now, it becomes that minus n lambda will be from the power it will become base into log e base e plus, for this multiplication we have to use plus. Now it is summation xi will come out from the power and will become base, and it will be log e base lambda. Okay, and this is nothing but, as you all know, that if we do log a by b, right, then this can be written as log a minus log b, because it's a division form. When there is a divisional form, then log is nothing but it actually takes both the terms and we are getting a subtraction form. So that is also can be applied here, that we can actually subtract log pi I to 1 xi factorial. Okay, so this is the general form of logarithmic transformation that we can apply here. And now I am going to do derivative, first order derivative and second order derivative to this log L of lambda function, and from that derivative we are going to obtain the value of lambda, that is the parameter, and that is the maximum likelihood estimator of the value that we will obtain will be the maximum likelihood estimator of the Poisson distribution. Now let me differentiate this log L lambda with respect to lambda. Okay, I am not willing to do here, but if I do here it will be very much easy for you all to understand. Now at first, when we are doing the differentiation, this term doesn't even exist, because log e base s is nothing but 1. This term has a minus n lambda only, and if we do the derivative of minus n lambda, what will we obtain? We will obtain that minus n will be present only, because lambda, whenever we are doing derivative of lambda with respect to lambda, that will be turned out as 1, so it will not be available or not be present. So lambda will be gone, we have only minus n from here. And from this portion, if we do the derivative of log e base lambda, then summation xi will be treated as constant, and it will be kept in outside form, it will be kept outside from the logarithmic transformation and from the derivative portion as well. We will do the derivative of only this log e base lambda. We will do the derivative of this part only. Now we all know that if we do the derivative of log x with respect to let me write this, if we do the log x derivative with the, if we do this derivative of log x with respect to x, then what will we get? We will get 1 by x, right? So that is very easy, we all know this type of logarithmic rules. So log e base lambda, if we do the derivative, it will be nothing but 1 by lambda, and this part doesn't have any lambda, so it will not be, it will be treated as constant. And if we try to derivative it, or if we try to differentiate it, then it will be completely converted into 0, and we will get minus 0. So minus 0 is not even required to be written. Okay, so that is what we have obtained here, minus n plus summation xi into 1 by lambda. So let me write this again. This is nothing but del log of L of lambda by del of lambda equals to nothing but we have obtained what? We have obtained minus n plus summation xi into 1 by lambda, minus n plus summation x 1 by summation xi, no sorry, not 1 by summation xi, summation xi by 1 by lambda, summation xi by into 1 by lambda. Now this is the first order condition, and this first order condition we will take it as equals to 0. Whenever we are taking it as equals to 0, then we will get the value of our parameter lambda, and after that we will, from the second order condition, we will try to satisfy that we are being able to maximize the function or not. Basically our target here is to maximize this log L lambda, and we all know that there are two steps that we have to follow. if we have to maximize any function. One is the first order condition will be equal to 0 and the second order condition should be negative. So we will do both the things. From the first order condition equals to 0, we will find out the value of lambda, and after that from the second order condition, if it is less than 0, then we will say that we have been successfully completed our maximization and we have obtained the value of lambda. Okay, so at first I will take first order condition equals to 0. So first order condition is nothing but it is this, so that is this also. So I may write it as minus n plus summation xi by lambda equals to 0. Now if I take this minus n on the right hand side, it will become summation xi by lambda equals to n, and if we take this lambda on the right hand side, it will become n lambda equals to summation xi. So we can write lambda equals to nothing but summation xi by n, that is x bar. Okay, so this can be written also as lambda hat denoting the estimated parameter of the Poisson distribution, or estimated parameter for the maximum likelihood estimation of the Poisson distribution. So our maximum likelihood estimation for the Poisson distribution is nothing but the sample mean x bar. So we have successfully derived the maximum likelihood estimator of the Poisson distribution. Now we will try to see whether this function is actually being maximized or not. So for that we have to check the second order condition, that is also essential. So I am going to write the first order condition at first, that is minus n plus summation xi by lambda del log L of lambda by del lambda equals to minus n lambda plus summation xi by lambda. Sorry, it is minus n only. Okay, now if we do the second order derivative of this function, then it will be del square log L of lambda divided by del lambda square. So minus n is a constant, so it will be 0 if we do the derivative with respect to lambda. But this part will have this part when we are doing derivative, it is nothing but it is at summation xi into lambda to the power minus 1, then it will be easier for you to do the derivative. Now minus lambda to the power summation xi into lambda to the power minus 1. Whenever we are doing the derivative, minus 1 will be taken outside, so it will be summation xi minus 1 into lambda to the power minus 1 minus 1. So now we have nothing but summation xi minus lambda to the power minus 2. So if I take this minus here, so that will be minus summation xi lambda to the power minus 2. Now lambda to the power minus 2 can be written as 1 by lambda square, right? So this is the term that we are getting when we are doing the derivative of summation xi by lambda with respect to lambda. Okay, so I have shown the calculation here. Now if I just put it into the equation, that what will be the value, then that is nothing but minus summation xi by lambda square, summation xi into 1 by lambda square, or you may write into summation xi by lambda square also. So you all know that this is a positive term, this is also a positive term, because it is having a square, so it has to be positive. This is basically summation xi, so it is also positive, right? So this entire term is depending upon this minus sign or negative sign, so that means this term is nothing but it is negative, and we can write that the second order condition is less than 0. It is being proved here. So we have successfully done the maximization of the function, and we have also found out the value of lambda, that is the only parameter present in the Poisson distribution, and that is the Poisson distribution having the maximum likelihood estimator as sample mean, that is denoted as x bar.